to start the recording.
Yeah, so there's some lag. It has started now. Okay, so yeah, so we discussed about word to vec, and also in the previous class, Sridhar has talked about RNN and the basics of that, how it can be used different language-related problems, and so on. So today, we'll try to cover one more word representation algorithm, and after that, we will move on to a new topic. So the other word representation algorithm that we uh, will cover today is called GLOVE, which stands for Global Vectors for Word Representation. It came around 2014. And again, we'll see that today or in the previous class also, when RNN was covered, you possibly saw that for every word, there's a base representation which goes inside the RNN. And inside the RNN cell, then uh, some outputs, two different outputs are computed based on the current state and the current input. So what to wake, glove, all those can actually be helpful for getting those initial representations. And since we rely a lot on these initial representations and hope that the system will pick on the correct modified representations as we go on, it is important to have the initial representation also to be something quite meaningful. Otherwise, the convergence and other things will become very slow. So that's why some good initial representations are always preferred, and what to wait glove are very good choices for that. So in what to wake, as you understand, or as we discussed earlier, that there's the context which influences the vector of a word, right? So based on the context word, we try to predict the target word and vice versa. Now in glove, the observation that people made is that many times two things can be in the same context due to various reasons. Sometimes the reasoning can be spurious, sometimes it can be due to some functional uh, or syntactical reasons. On the other hand, there could be many ways or many reasons where due to semantic kind of information or reasons, the words are together. So they say that uh, instead of seeing whether two words in the same context, we let us look at what are the other words that these two words co-occur with. Okay, so for example, here we are looking at these two words ice, steam, or these words ice, steam, solid, gas, water, and fashion. So ice and solid, these two words will occur together maybe many times. Okay, ice and water, maybe that also will occur together many times. But ice and gas and ice and fashion, so these two are not likely to co-occur together many times. So if we know that ice and water is co-occurring many times, and at the same time steam and water is also co-occurring together many times, then water is a word that actually binds together ice and steam. And since there are many such pairs, there are many such instances where ice water, steam water, they occur together, most likely ice and steam will be similar. Okay. On the other hand, if you look at the word fashion, fashion does not go together with ice many times, and fashion does not go well together steam also many times. So they are very unrelated. Now, now if you see that solid and ice, these two words will occur together many times, but steam and solid may not go together that many times. Then steam and gas, on the other hand, will co-occur together, but ice and gas will not co-occur together many times. So if you look at all these different combinations, and suppose we are looking at this pair ice and steam, we can identify a few probe words or anchor words and see how well my words of interest like ice and steam co-occur together with the probe words like solid, gas, water, and fashion. And then if you look at these probabilities, let me see how to turn on the pen or pointer. Okay, so I need to figure out how to add scripting to it. So, all right. So we focus on this ratio of co-occurrence probabilities, okay, which is there on the third row. So for water, for k equal to water, we see that the probability is 1.36, which is very close to 1. That means, these co-occurrence probabilities are both either very low or very high. For 0.96 also, it's very close to 1, which means the co-occurrence probabilities k given ice and k given steam. So these two are again very low in this case. So two very low things, we are taking the ratio of them, it is coming close to 1. On the other hand, if you look at the first two columns, where the ratios come out to be 8.9 and 8.5 into 10 power minus 2, so point say 0.85. So these values are either very high or very low. That means the probe word is close to one of those words. Now, this way, you can actually find how the binding of the different words together. And using this, there are a series of mathematical steps and so on, so that finally the objective function is reached at. Yeah, and finally the objective function here comes out to be, there are many series of mathematical steps that I'm skipping. The last row that you see here comes as the objective function. Now, how to interpret this? So suppose we have two words I and J, and based on our collection, we will compute Xij, which denotes how many times they are co-occurring together, or co-occurring means together. So how many times they are co-occurring. Okay. Now, this Xij will try to model using some latent vectors. So if you look at the equation, the first equation, which is in the third bullet, so the right hand side is log of Xij. So this Xij is the count that we get from the corpus, that is, it's an observed variable. On the other hand, the left hand side contains wi, wj hat, bi, bj. So all of these are some variables that we are trying to learn. So wi is the vector for the first word I. Wj tilde is the vector for the second word second word j, and bi and bj again correspond to two bias vectors from the words I and j. So the first part, which is where we see a multiplication wi dot wj tilde. So this actually tries to model the interplay between the words. Okay. On the other hand, bi is something which is an intrinsic property of I, and bj tilde is again something which is an intrinsic property of j. Now, using these things together, we are trying to model xij. But xij can have very large value, very small value, so that in order to make the learning a little simpler and not very noisy, log has been added. Okay. Now, if we have this, then the objective function, you will see that there is a square term. So the difference between the left hand side and right hand side, there is the prediction on the observation. So these two we want to minimize. So that's there as the squared loss. And then we have before it something called fxij. This fxij is nothing but a scalar, so which depends on the count xij, where if the count is very high, this f will be higher. If count is very low, this will be lesser. So the idea here is that uh, for each ij pair here, we are trying to find this prediction. However, the words which are co-occurring many times, for them, we give this a higher weightage. On the other hand, the words which are co-occurring less number of times, for them, the weight is less. So if you look at the summation, this summation is not over all possible token pairs. Okay, this is all possible terms or word pairs. So we see the summation is for I and j equal to 1 to v. So if there are v number of words in the entire collection, so we see to these many pairs we are operating on. Okay, so if two words I and j are co-occurring many times, for them we want the prediction to be more accurate. So this f value is high. So if the prediction is more, it amplifies and the overall loss actually is bad. On the other hand, words which occur less number of times, we can afford to have a larger misprediction error on that. So this is how this objective function has been defined. Now, my question to you is that can you predict whether we are going to maximize or minimize this objective function? So the question is, this is the objective function. Are we going to maximize it or minimize it?
So minimize it.
Minimize it, right? So since it is a prediction error that we are measuring, we are minimizing it. So finally, as word2vec gives two representations for each word, right? Here also we get two representations of each word, and these are the W and W tilde, these two matrices. So this is how Glove learns the representations, and this came from Stanford University. And this model, then people applied this Glove model on many different corpus, many different corpora. So on news data, people applied Glove. On Twitter data, people applied Glove. And there are many other large corpora on which this was applied. And the pre-trained models were also released. So here the pre-trained models would be like a dictionary where you have the word and the corresponding vector. Then the vectors also can have different dimensions. So again, there were yeah, these models for different dimensions, like dimension equal to 100, 300, and so on. Okay, so that was about love. Now let me move on to the next part, which connects with these embeddings. See all these representations that we get, right? The W tilde from love or W prime from word2vec. So can anybody tell these for getting these representations, we are doing some learning, right? Now, what kind of learning is it? Is it supervised, unsupervised, or any other type? What type of learning we are doing here?
So like supervised.
Yeah, semi-supervised.
Okay. Supervised, semi-supervised, any other? So, all right. So in case of supervised, what happens when we say that, okay, it's a supervised learning? So for each example, we also provide a label, right? And who provides this label? Who comes up with this label? Suppose we are talking about sentiment analysis. Okay, so there is a piece of text, and then assuming that we are trying to identify whether the sentiment is positive, negative, or neutral. So against the text, one of these three labels is assigned: positive, negative, or neutral. Now, to create this training data against the text, who provides that label? How do we get that label to create the training data?
So it's already available beforehand, like user output
When we
rating.
say
Yeah,
already available, so
yeah.
I mean, how has it been available?
So the right hand side of the equation in the previous slide, it was a count. So that count is not a supervised count as such.
So we'll come to
It
that. We'll come to
depends
that.
if
So let's address this question first. So sentiment analysis, we are going to train our sentiment analysis model. So for training, we need a text and the corresponding label, right? So how do we get that label? I mean, one can say if the data set is available, we train on that. But suppose there is no data set given, we are trying to come up with our own data set. In that case, how do we get the label?
the human sits and basically tells which is a positive or negative sentiment.
Right. So mostly it's some human who will assign the labels. And in case of unsupervised, how will the thing differ? The label will not be there, right? Now coming to this part, and as he was mentioning, that xij, this count, that we are trying to match, right? So this is the target of xij. So xi is the target value. Now this xij, who provides that? There is no human who says that, okay, this word I, this is the word j, and this should be the count, right? So this count can be obtained by running a script, by running an algorithm. Right? Similarly, so if you remember word to vec, and let us take any of the models, skipgram or continuous pack of words. So given the context, we are trying to predict the target word. So who gives us these context words and these target words? Do we need any human to say that, okay, these are the context words and this should be the target word? So this question is a yes, no question. So
No, sir. We can directly get it from the data set by maybe running that context plant window and create the training set.
we can obtain it programmatically, right?
Yeah.
So in other words, the supervision signals for glove or TUVEC, these are not provided by any human. We do not require human for this. So they can be obtained programmatically, and this program which creates this training data in these two setups can be part of this or is part of this entire training process, right? So you have a corpus that is your starting point. Now, when you are trying to learn what to wake or club, firstly, from that corpus, you obtain your supervision signal. So in case of what to wake, it will be the target words and context words. In case of glove, it will be the count for this pair. And now that gives us the target level for the associated input. Then the algorithm learns on this. So that's why these scheme is called self-supervision scheme. So both word-to-vec and GLA are self-supervised learning algorithms. Yes. Yeah, so there's an important point to remember, and most of the modern language modeling and other kinds of tasks that we are looking at least for the pre-training tasks, and we'll possibly discuss in detail later what we mean by pre-training and other things. So here the annotations are obtained programmatically. And that is why it is possible to learn these algorithms on huge amount of data. So in case a human had to provide all these labels, our training data would have been much more smaller. And due to that, so due to that, the models would not have been able to learn from a large number of examples. But here, since that restriction is gone, they can actually learn on a large number of examples. And then, by virtue of seeing a large number of examples, whatever knowledge they come up with, okay, whatever intelligence is there in the parameters learned, so those are a very good starting point for many other downstream applications. And this is why this kind of pre-trained models can actually be used by anybody for any downstream task, but depending on the nature and difficulty associated with the task, the performance may vary. But these are very good uh, ways of learning some world knowledge, at least till some level, from large amount of data. Okay, so now taking this point forward, that suppose there is a collection and there is no regulation by any human, and based on the data, the model is creating its training example and learning things. So will it be always good, or there can be some scenarios which need attention? So that's what the next topic or subtopic deals with. So there were studies where people saw that these embeddings that we learn in this way, they reflect some societal bias. So what does it mean? So we remember that the word analogy task, right? So there was an analogy task where Paris is to France is equivalent to Tokyo is to what? This X. So what will X be?
Japan.
Japan. And why so? Can you give the reasoning?
Then those are similar words, Perry. The vector, the transformation which is needed to reach France from Paris is same as it would need to reach Japan from Tokyo.
So this transformation, I mean, you gave the answer Japan, which is actually a correct answer, but it did not compute the transformation, right? So why do you think Japan is the answer here?
So like we can take the difference, vector difference between France and Paris and apply that on Tokyo
But
and
you did not do
see.
that, right? When you gave the answer Japan, you did not do this computation. So how did you say Japan?
The capital city.
Right. So the relation
Yeah,
that this thing is capturing is country and capital. So or say
yeah.
capital to country. So uh, yeah, so we know that, or we expect rather, X should be Japan here. And then if we actually do what you just said, find the difference and then see what are the words which are aligned with that and so on. So we'll expect Japan to be very at the either at the first position or at the very top in that list of predictions, which is true. Now let us look at something else. Father is to doctor is equivalent to mother is to what? I mean, what is our guess? So this model gives nurse. Hmm. Now this is somewhat debatable because we can have male nurse also. Now then there was another probe that they did. I mean many other probes that they did. So is man is to computer programmer is equal to women is to what? And then the response that they got was X equal to homemaker. And this is not one example. They got many such examples which were a case of stereotyping. Okay, so again, to be a disclaimer here. So we are not saying that okay, computer programmer is much more superior than a homemaker. So there are many different aspects. I mean, there can be many. Yeah, I mean, both the task, computer programmer and homemaker, have their own characteristics, and one needs to be really, really great to be good in both of this. But we're not saying, okay, one job is superior and another task is inferior, but we're trying to see that there is some kind of gender-based stereotyping that we are seeing here. So they did many such other examples. And if we have something like he is to she, and let her figure out how to bring the pointer here. Uh, so if we say that she is to he equals homemaker is to what? The answer becomes maestro. Again, she is to he, then She is to he is equivalent with, look at number 4, librarian is to what? Answer is philosopher. So if you look at, the words here, say homemaker, nurse, receptionist, librarian, socialite, hairdresser, nanny, bookkeeper, stylist, housekeeper. Somehow there is a notion in the society that these tasks are kind of inferior or require lesser skills or are easier to perform and so on. On the other hand, typically in society, a large or a higher respect and repute is associated with the terms that we see towards the right hand side. Now, then they said, why is it happening? Now, if so these are actually produced by the algorithm. Now, when something is produced by the algorithm, which is trained like that, either what could be the reasons behind that? Either the system has not learned properly, or the data itself was like that, due to which this kind of uh, information or notion which is there in the data, they got surfaced up. Right? So, uh, so that was the observation, and that was the yeah explanation that people gave, that if we are disturbed by seeing these kinds of results, this kind of stereotyping, either the data is bad, or either the data is not proper, or there is something which is coming from the data, or the algorithm is not right, due to which this is coming. But then they said that in the algorithm, we didn't do anything special to favor one gender or something like that. So it was self-sort by scheme, right? So nobody provided any examples to it. And the procedure to extract the training examples, and also if you want to evaluate the evaluation examples, so those could be automatically obtained from the data. So that means there is some kind of quote unquote bias which is there in the data, which is just being amplified when such kind of techniques are applied. Okay, then there are a few other gender stereotypes and other things also which are there, and there could be some gender appropriate she he analogies also, where she he same as queen king, waitress waiter, sister brother, these are okay, right? So suppose this is the behavior and we say that this behavior is not right, then what should we do? So what is your recipe? That if we want to remove the societal bias, what should be our step? Should we try to fix the algorithm? Should we try to fix the data, or what?
Data is the first step.
Okay. Anyone else with any suggestion?
But we are anyway going to train with a lot of data. So we are not sure actually which segment of data is leading to such kind of result. So maybe some changes in algorithm.
Okay. Anybody else?
Then change the mapping pair. That is also changing the data, kind of changing the data itself.
Say again, change the mapping pair.
In the last slide, we saw that mapping pair where the father was doctor. We can actually change some, pairs like this in our data.
But there's only to probe, there's only to, I mean, we are applying this to see what the algorithm is predicting after the learning has already happened. So if there is some bias which is there after the learning, irrespective of what probe we give, that will be there, right? It is something like there is some bad content, but we don't give query to extract it. So we need to see how to avoid that kind of bad content only. Okay, so both of you are correct in some sense that we can try to modify our data and ensure that these kinds of things are not there. On the other hand, identifying that what are the things, what are the different disturbing things that we could come up with. Enumerating that becomes difficult. Now, suppose we could understand that also gender is one that we try to avoid, but we do not know where in which form the gender-based thing is there. So there were some examples where somebody said that They were using some technique to go through the job applications and the CVs and try to predict whether the person will be suitable for a job. And what they saw is that the female candidates, in most of the cases, the algorithm was saying no to. Then they say that there's definitely a bias because they also had and they also wanted at the same time they also felt that women are suitable for the kinds of jobs that they were having. So they say that okay, anything that was there in terms of the gender, they will remove. So they removed this thing. They removed the gender female that they removed, and there was one more thing that they tried to remove. Okay, they removed the gender, and still the performance was very similar to earlier. Then they saw that there was some gender-based information already was there. For example, schooling, when they said girls' school was mentioned. Then they said, okay, for everybody, we'll remove the school also. Then they also saw that okay, situation has not improved much. So how? Then they realized that when the people are writing hobbies, right? There are hobbies where nowadays things might be changing. This is I'm talking about some scenario which is some 7-8 years earlier, where a lot of male candidates in their hobbies they wrote cricket, football, chess, carom, and so on. And for females, the hobbies were different. There were hobbies like swimming. There were hobbies like cooking, gardening, and for female candidates, those hobbies were occurring more number of times. So we can try to fix the data, but we do not know exactly where, in which form, these all information might be present. So, so then people said, then is there a way in which we can either modify the algorithm, or if the algorithm is very simple and we acknowledge that it is very powerful because it is self-supervised and a lot of things can be learned. So can we also do some kind of post-processing? So then they try to look at that angle and try to have either some kind of post-processing to remove the gender bias. So what I'll be covering is only one way of post-processing the data, but there are quite a few other number of ways in which these algorithms can be, this debiasing can be done. Okay, so
So I have a question regarding the same. Now,
yeah,
how to identify that which classes to remove? Like, we proceeded with gender, school, or hobby. And second associated question would be, because if we generate a kind of a graph, matlab, one kind of, these are, you know, kind of mappings, multiple one to many mappings are formed. So they may be, underlying different tokens which are responsible for that, those mappings. So how we will be dealing with that?
so that's why you know uh, that's why modifying the data, filtering the data is not very effective due to the reason that you just mentioned. We do not know where, in what form this information will be there. So let the algorithm run on the existing data, let it produce something, and then we'll do some kind of post-processing to correct it.
So which keys to identify, which token to identify to, proceed with the post processing? How to identify that?
We'll talk about that.
Okay.
Yeah. Okay. Now,
Sir, I
connected.
also have
Yes.
one question. I have question on the formulation of this problem itself. Like we subtracted this log of xi, and there is a function of f of xi. How did we come to that? And actually, when we find the loss, it's like y minus x, but we have w plus b minus log of xij. How do we say that that is the loss there?
You're talking about this first equation here, right?
Yes, sir.
See, xij is the target. So we are trying to match the co-occurrence count. So the idea is that if we know well about the vectors, the words themselves, we should be getting a good idea about their co-occurrence. For example, ice and steam, ice and water, ice and fashion, we know that there are some counts which will be low, there are some counts which will be high, so which will be high. So we're trying to guess by looking at the words. Now, if we have a good idea, in our brain we know what ice means, or what fashion means, what water means. Accordingly, we have some idea about the scale of xij. So that same thing we want to train the model to learn. Okay. So this w I w j b I b j are those representations. So to give an analogy, so some of you might be aware of the rating prediction task in movie recommendation. So often people give ratings to different movies that they have watched. So in IMDb, we see that, okay, ratings are there. Even in case of products in Amazon or any e-commerce site, we give ratings to products and so on. Now let us come back to movie recommendation or movie recommendation rather. So where uh, suppose there is a person who watches lots of movies, we know what different ratings the person has given to different movies, and then we want to see what rating he will give to a new movie, say 12th Fail. Hmm. So then people say that there were many such many techniques which were proposed for that, and one very nice technique which came up and which was one of the best performing techniques. So there they say that there are some movies or which will so for example there is an affinity between user and movies. Okay, so here let us assume that we do not know any other information like the movie genre, who is the director, actor, and all those. So if user, suppose there is a vector for the user and there is a vector for the movie. Now if the user and the movie, there's a very good affinity, very good association between these two, that component should be high, and that's why the rating also should be high. On the other hand, there are some users who are always very lenient while rating. So any movie that they watch, they'll always give very high rating, irrespective of how much they liked. Now in that high rating, there can be some ordering, but still they are very heavy rated. On the other hand, there are some users who are very, very strict. Even if they like something very much, they will give it a low score only. Out of say 0 to 10, even if they like very much, maybe they'll give 7 or 7.5 only. So the final rating, if we try to see, it depends on many factors. Firstly, the interplay or the connection between the user and movie. Then there is some property of the user, his rating pattern, and also something about the movie. Say, for example, if there is a popular movie like Titanic in those days, or say some very popular movie now, the movie itself, the fact that the movie is popular itself will bring a lot of high viewership and rating. On the other hand, a movie which has been rated as bad, that rating also will pay. So this entire rating prediction, suppose the final rating that we want to predict is R, which in this case is say 9 for a user and movie pair. So this rating, they want to they decomposed into three parts. Firstly, user and movie, so their interplay, their affinity, then some property of the user, which is called the bias of the user, and some property of the movie, which is something we can say the bias of the movie. And these three things together, they saw can explain the movie rating pattern very, very well. Now here also we are seeing something similar. So WIWJ somehow represents the association between the words. If they are very similar functionally, they come in the same topic, same domain a lot of times. So that way their vectors will try to align so that this Xij count is higher. On the other hand, there could be some words which are very highly likely, maybe because it's a domain specific corpus or the word is very prominent, and the same thing may happen for J also. So that's why these three things are there. They together uh, uh, should be able to model the prediction, should be able to model the actual observed count Xij is what the belief is. And how this one explanation of this, but exactly how we came to this formulation, and there are a series of mathematical computations and tricks which are there in this paper, which is hyperlinked here. You can also go through that. So did that answer your question, Abhishek?
Yeah, yeah. Yes, it is. Just one last question. Like you talked about embedding also. So, like, is the input here embedding, like as we had in earlier case, or it's just the co-occurrence probability Xij?
So Xij is a matrix, which is the co-occurrence, and each of these Wi, Wj, Bi, Bj are column vectors, and they are initialized with random seeds.
Okay, but it will learn the this your globe, right? So it will learn the vector representation of each and every words. So I think this Xij, does it represent in some way those vector what it will learn at
Xij
last?
is scalar count.
Okay, so then I am not able to link here that how it will learn those representation, those vector representation,
Okay, so
because
Bi,
Xij is scalar.
so Bj, sorry,
Yeah.
Bj are scalars, and Wi, Wj as vectors of same dimension. So this dot product will give you the
Oh,
scalar, and Bi, Bj are scalars. So together you will get a scalar.
okay. Okay, that makes sense. Thank you.
So can you just repeat why there is a need for BIBJ values? Can't we, we are solving like a matrix factorization problem, so we could have done away with the just Wi Wj vectors, and then there's the actual value of that. So the mean squared error for that. So the final value would be the loss function. So why there is a need for BIBJ here?
There is actually, if you remember when we started this discussion, we talked about three different things, right? The word ice, the steam, and a probe word. Right? But in this formulation, we see only two things, I and j. The third one is gone. Right? So if you look at the
Okay.
derivation, somehow this third word is absorbed in this computation. So yeah, so this ratio of probabilities, there is something like log xik by log xi. So this I we know, this xik, sorry, this xik we are trying to model, but this log xi, it comes inside, and that comes inside this bi. And yeah, so this derivation, we'll see that there are some terms which are left out, and that is absorbed inside bi.
Okay.
And symmetrically, bk also comes in.
Okay.
Sir, when while computing Xij, is it just a co-occurrence pair like I plus one pair, or we also consider some filter, like if uh, water is hot, some word, something like this is written. So do we also consider some filter size also here while
You mean
computing Xij?
sliding window size?
Yes, sir. Yeah, sliding window. Yes.
Hmm. So right. So how we define co-occurrence, that is in our hand. So one can say in a single document, if two things come together, therein we consider that they co-occur. So we can say if in the same sentence they come together, they co-occur. Can also say that if inside the same sliding window they come, they can co-occur. So there can be different models for this co-occurrence. You're free to choose anything. So yeah, so we can check the paper exactly what they consider. Most likely they considered document, but we can be
Okay, sir.
we can check that.
Okay. Thanks, sir.
Okay, so let us go back to the debiasing thing. Okay, now identifying and quantifying bias in the word embeddings, that is so this part, as we had a question earlier, that they should, I mean, which words do we consider? Say, for example, here we had a this, right? So when we look at the example, when we look at the process, we'll come back to that list again. So assumption is that the aspect of bias is known, it's a gender. So we need to first find the gender dimension. What does it mean? That each word is a vector. And when we say vector, we can consider that, okay, there is a point in that huge vector space. Or we can also say that there is a vector. I mean, that point, if we connect with the origin, right? That's a line kind of thing. That's a vector that we get. So similarly, there should be some line some direction that corresponds to the gender. So we need to first find that. How to do that? So we collect explicit gender-based word pairs. So we know, it's our assumption that we know the aspect for which we are debiasing, say gender here. So we ask crowd workers to give us gender-based word pairs, FM pairs, female male pairs like woman man man, mother father, girl guy, and so on. So this is very easy to get, right? So maybe 10, 20, 100, such a list we can curate. I mean, 100 may be difficult, but yeah, 10, 20, this should be easy to obtain. Now, from this, we try to find the gender dimension. What is that gender dimension? And how do we get that? So what we do is, so for each of these words in each of these vectors, we can get the dimensions of each, right? Or we can get the vector for woman, we can get the vector for man. We take the difference, we get F minus M for that pair. Then for mother, we get the vector, for father, we get the vector. We can get the dimension F minus M for that pair, and so on. So if we have 20 such examples, we get 20 such vectors, F minus M vectors. Now from that, we want to extract the gender dimension. So what they did is, from these observations, they did a principal component analysis. Okay, and in the principal component analysis, the first dimension, which is the dimension covering the largest variance, that they said is the gender dimension. And why is that the gender dimension? They also gave a reasoning for that. This dimension they got from these gender-based pairs, and they considered many such random pairs. And for them also, they got the first principal component. So what they saw is that, if the vector that we construct from these F minus M's, corresponding to that, the eigenvalue is the highest, and very rapidly the next eigenvalue taper. So on the other hand, if you look at the principal components that they get for random pairs, so there the eigenvalues are actually not coming down this randomly. So that made them believe that the dimension that they have got from this exercise, that is actually representing the gender. And later experiments that they conducted also seem to support their claim. So then this is how the gender dimension has been obtained. Now you collect a set of n gender neutral words. Now these gender neutral words could be like, say footballer, uh, and different other gender neutral words which could be there. Then from these words, you get the gender component G. How to get the gender component of this word? So you know the gender dimension. You know the representation of one vector, say W. And if you take the projection of W on the direction of G, that is the gender component. And what is the strength of that gender component? That can be the length of the projection, the size of the projection. So that is size of cos of WG. Now this projection you sum over all elements from your N. And then you take the average. So this gives you the direct bias as measured with respect to that set N. So suppose you come up with a word embedding algorithm. You can first collect a gender-based word pair. Multiple gender-based word pairs. From that, you can compute the gender dimension. And then you also additionally have a probe set where you have words which you want to be, not having any gender component in. So for those words, you see their projection length on the gender dimension. Take their average, and whatever is the final value that you get, that represents the direct bias in terms of gender existing in this learned model. So if you have 10 different learned models, you can see which one has the highest gender bias according to this. So this is how we can quantify the bias. Now, after we quantify the, then the debiasing techniques could be there. Yeah, so again, inside summation, what we have, we can also raise it to power of C and do many different things. So they showed some results that is possibly in the next slide. So if you look at the words here towards the left column, teacher, bookkeeper, receptionist, registered nurse, waitress, and all that. So, and the percentage figures that you have are the components on the gender bias. So for some words, there is 0.67. So receptionist has 67% in the gender component. So businessman also has 31% in the gender component, and so on. So yeah, then they said, okay, this is direct bias. That could be something like indirect bias also. If you remember from vector algebra, so if there is a vector saying 2 dimensions, so x we can represent as x1 into I plus x2 into j. So there are two orthogonal components, I and j. And each vector has two components, one along I, another along j, right? So similarly, there is a component which is aligned with the gender component. Suppose the gender component is I, and the perpendicular to it, whatever is there, so which is the non-gender component, that is j. Now each word w will have one component in I dimension, one component in j dimension. Okay. So we need to find the component to the perpendicular of the gender dimension. So component of the vector, I mean, these are some basic vector algebra. Scalar component is a dot b divided by size of b, and vector component is, the previous one, dot b. So the first part is a scalar, a dot b is a scalar, and divided by size of b, that is also a scalar. So it's a scalar component. But the vector component is that scalar component if you multiply with the direction. Now b is a vector, which is a direction. So and it's a unit vector actually. So that one. Now for w, you can now get these two components, wg. Wg is w dot g into g. So w dot g is the scalar, and then when you multiply it with g, it is the scalar according to that unit vector. And then w perpendicular is the w minus wg, the leftover component. So then based on that, the indirect bias could be compared in the formula. I'll check the formula. Yeah, so essentially, based on these, you can actually compute how much is the gender bias and how much is the indirect bias. And what you can do is, since the perpendicular of the direction, since the perpendicular, there is no projection, right? Projection length is 0. So that can be considered as the dimension towards which you can go. So what they did is that, suppose we are talking about the objective function of gloves. With that, we are adding two terms in the regularization. One term is that lambda cos wij, and then gamma cos wjg. So assume that you have already learned the vectors. From these vectors, you can get the g, the gender dimension. And now you're trying to see how wi aligns with the gender dimension, how wg aligns with the gender dimension. Okay. So, and if you remember, this overall thing was an objective function. So this alignment we want to reduce. So this is some kind of post-processing technique which can debias, which can be used to debias glove.
Sir, one question on that PCA part, like, do we calculate PCA on the vector what we obtained for each and every pair?
Yes, this f minus m you get for each and every pair.
Okay, and every pair we calculate the PCA.
But
By
no,
keeping into the vector. Like creating a matrix out of those.
Yes, yes. So if you have say 10 such pairs, for 10 such pairs, you will give 10 such vectors, stack them together to get a matrix 10 cross D.
Okay. Yeah.
That will
So
be
now
similar.
we got gender dimension from the principal component, but now we are considering the like gender neutral word. So
Mm.
this gender neutral word, if you take the projection into the gender dimension, that will be very small or negligible, right?
That
Because
is our
this vector is
expectation. That is our expectation. But what we saw earlier is that there are many gender neutral things, I mean, which we want to be gender neutral, say architect, philosopher, but they may still have a very high projection along the gender dimension.
okay.
So that's why this quantifies the gender. And our N can actually can actually contain a set of all such words, which we know and we want to be gender agnostic.
Okay, and at last we added this our calculated gender dimension by this cos and wi and g into the formulation itself, but we are not doing any retraining, right? It's just like while we do the inferencing, we add this into the output. Yeah, this part
No,
and lambda
this
and
this
gamma.
will be retraining only. This will be retraining. First, you train the original graph
Oh, okay.
and this one. The other thing what you can do is you do it for a batch, recompute G,
Mm-hmm.
and then evaluate it and do it in a loop multiple times till you see that okay, this stabilizes.
Oh, now if we are doing retraining again on the same data, then it can again learn the same gender bias, right?
We're trying to minimize it. So if you see that okay,
Oh,
this bias is still very high, so there should be a way to bring it down by doing this gradient descent.
yeah, it makes sense.
So
Yeah,
consider
thank you.
this to be a regularization term. So we have this, right? Lambda,
Yes.
say wi square.
Yeah. Mm. Thank you,
Yeah,
sir.
Samir has a question, right?
Yeah, yes, sir. Sir, when we are saying there is this gender-based dimension, and then there is a projection of that dimension which corresponds to the gender neutral words, right? Uh, the projection is the for the gender neutral, right?
Uh, so for the gender neutral, we want to actually probe, is it really becoming gender neutral or not? So any vector we can actually project around that dimension. But to quantify, we are more concerned about it's something like a test set against which we are checking the gender bias. But any vector we can project along the gender dimension.
Okay. And this on the screen, which objective function is there, this only takes into consideration the gender-based or gender neutral as well.
So
This.
this summation is over I j equal to 1 to v. So it's a for all words in the vocabulary.
Okay. Okay. Thanks.
So this is from the paper which I have linked in one of the earlier slides. So uh, so there is bit of mathematics, but there is a lot of explanations there in the paper. So you can actually have a look at this one, which is from NeurIPS 2016.
A glove original paper, right?
Sorry?
A glove paper you are referring to. Uh,
No. So this is the one from 2016. Oh, I think there is some lag. This one is not yet there.
I
So when I'll share the slide, it will come on. Let me try to share from here itself. Hmm.
White screen, nothing is being shared actually.
This one.
Okay, sir. Yeah, we'll refer to that, and if there are any questions, we'll come back. Yeah.
And the so here you have the list. There is the explanation regarding the eigenvalues. And these are for debiasing algorithms and so on. So, I mean, there are many things which are which you have skipped, and determining gender neutral words, debiasing results.
Sir, is there no mention of any result in this paper for showing effectiveness? How?
They have here
Okay.
something like there are some graphs which are there before and after debiasing, the number of stereotypical and appropriate analogies before and after.
Okay.
And there is an appendix where they have the details. Yeah, so this paper has many versions. This is a shorter one. There are other versions as well. So yeah.
So if we want to remove multiple bias, then we can keep on adding uh, the
Regularization.
extra regularization for that specific bias in the loss function, right?
Yeah.
So
Instead of
this
post-processing,
paper,
if there
yeah.
is something where the model itself can learn the debiased results, which would be better, but hopefully there will be some algorithms also. My survey was not very thorough, but I'm sure there will be techniques, even for projection and other things. You learn and then you project to a different space. Something of that sort would be there. This is another version of that same paper, which is a little more detailed in places. So this result went up in the other paper. Direct bias, indirect bias, and some discussion. And yeah, in the this here they have the appendix. It's mathematically a bit involved towards the end, and yeah. Software debiasing. Words which are gender specific. how they had a questionnaire to come up with the list from crowd workers. Yeah, then there was a yeah graphical representation also of the same thing. Yeah, this. So this is the he direction. This is the she direction. X is a projection onto the difference between the embeddings of the words he and she. He and she is the dimension. Y is a direction learned in the embedding that captures the gender neutrality, the orthogonal dimension here. Gender neutral words above the line, gender specific words below the line. And among the gender specific words, words which are towards the female gender, which will be here like actress, girls, queen, sisters, and the ones which are towards the masculine gender, which come here. But they are gender specific, so they come below. These are okay. It's okay to have this kind of segregation here. But here, if brilliant, genius, these things are coming towards the C dimension, that is definitely a biasing. So these two versions are linked from here. This is the main paper, this is the detailed version. Okay, so any question, any further questions here? All right, if no questions, then we can go for a break now. It's 9:14, so we can come back at 9:30 and yeah, take up the next topic.
Okay, sir. Thank you.
So can we no, if after reading the paper, if there are any doubts, can we discuss it in the next class? Uh, uh,
Okay, yes, we can take a few questions in the next class.
yeah. Okay. Thanks.
Okay, so let us continue our discussion, and we will now start a new topic, so which is language modeling, and it is very essential for different natural language algorithms, natural processing algorithms now. So essentially, getting a better understanding of the language is possible if we have a very good natural language modeling scheme. So let me open the keynote version so that I should be able to edit it. Yeah, so there is some lag due to which the slide is not yet visible, possibly. Yes, so language modeling, so we assign probability. In language modeling, we assign a probability to a text segment or a sequence. Okay, so for example, if we have a sentence like if you have a sentence like yeah, the sky is blue. Okay, so there should be a probability that we should be able to assign to this sentence. For that matter, any sentence that is given to us, we should be able to assign a probability. But then why to do that? Why? What is the benefit of doing that? So it can be useful for many small tasks or applications. One example could be like spell correction. Suppose we have these two sentences. Okay, have you seen this before versus have you seen this before? Now suppose the user is typing this, and then there is an algorithm which says that instead of seen, we should be use this spelling seen. So we can actually check which one of them has a higher probability, and accordingly we can suggest. So somehow, so if this statement is there, we see that the probability is lesser with this, and this has a higher probability, then we can suggest that okay, you use the first version. Then for speech recognition also, it can be very helpful. So in this example, suppose the utterance is being converted into speech, into text, and the utterance has been captured like this: the waiter came running, and another possibility is that the water came running. So since the probability is higher, I mean, assuming that our language modeling is done perfectly, so we can expect that the probability associated with the second version is much higher than the probability of this. So accordingly, the system can also correct the text counterpart for the speech uttered. Then suppose there are algorithms which are generating text, and in that generating text, during that generation process, suppose there is one generation which is like this, the longest person on the earth, and another generation is like this, the tallest person on the earth. Okay, so we can actually identify which one has a higher probability and retain that. Now we can also think of having this language modeling as an evaluation measure for different algorithms for spell correction, speech recognition, evaluating generating text, and so on. So yeah, so given two models, we look at the things which look at the suggestions given by them, like this or this or this, and we can compare the suggestions given by multiple algorithms to do a benchmarking as well. Then we can also make use of language modeling for other tasks like matching query to documents. So for query to document matching, there are many different ways in which the score can be defined. The matching score between query and document can be defined.
And one of those methods is called language query likelihood model. Query likelihood model. So here the system assumes that the user, when he or she is typing a query, has some document in mind. Okay, and depending on what he or she expects in that target document, expects to find in that target document, the keywords are chosen. So if we have different documents, for each document we can get a language model, M1, M2, M3, M4, M5, and we can check the document which can generate the query, the document model which can generate the query in the best possible manner, or the highest probability of the query given the model. So then that document should be high, scored high. So essentially this probability also can be considered as a scoring mechanism for such kind of systems. So there are many different scenarios, many different applications where language modeling can be used. And what is language modeling? Language modeling assigns a probability to the text segment or the sentence. Okay, so now let us look at a few other sentences. Let the slide come on the screen. So suppose these are different sentences. Let us forget about the exact application for which it is being used. But there are amazing ladies and gentlemen in the class. I just had a delicious tea. The tale of two cities, large winds tonight. What's the name of this person? So all these sentences uh, possibly should get lesser probability in terms of their from language modeling perspective. But now the question is, how do we assign these probabilities? All right, now let us say the sentence is W, which has n different words, W1 to Wn. Okay, so this is our sentence, and language model deals with finding the probability of either observing the entire sentence, that is probability of W, or seeing the next word given the previous words. That is, suppose the next word is Wn and the previous words are all observed. So based on the observed words W1 to Wn minus 1, can we predict the probability of the next word? So although these two objectives are different, the first one we are observing the probability of the entire sentence, and the next one where we are trying to find the probability of the next word given all previous words. So although the objectives themselves are different, but they're connected with each other. Can anyone throw some light on how we can connect these two probabilities?
Sir, can you please repeat the question once?
So we say that language model deals with finding the probability of one, observing the entire sentence, and probability of seeing the next word given the previous words. So obviously these two different probabilities are different. We're trying to measure two different things: entire sentence versus next word given the previous word. However, although they themselves are different, there is a connection between these two. So can we establish that connection? Can we identify that connection?
PW, if we loosely connect, the PW is the joint probability function of PW and W1. Like all the words in the PW.
Yeah, we can use a Bayes theorem to
Yeah.
link them together.
Chain rule also, I think we can use it, sir.
Right. So all answers are correct. So these two can actually be connected. So that's why we can use any either of these two definitions when we talk about language modeling. Now, now let us stay with this definition now, or not this definition, this task now. So we need to know how to compute this probability of Wn given W1 to Wn minus 1. Okay. So let the next slide come up. Okay, so you mentioned chain rule. So let us see how chain rule, how we can use chain rule to write the expression of Pw1, W2, W3 till Wn. So we'll start with Pw1. Essentially we can, we'll start with Pw1, assuming that there is a sequence in which the words are there. W1, it's not and like W1 and W2 and W3 like that. It's a sequence that we are talking about. So the ordering is also there. So Pw1 into Pw2 given W1 into Pw3 given W1, W2, and like that till we reach the last one. So going by that assumption, the probability of go to school would be like probability of go multiplied by probability of 2 given go into probability of school given go and 2. Okay, so we saw that how the two objectives can be connected. We saw that how the entire probability, finding that entire probability of the sentence can be expressed as a chain rule. And we saw that given an example sentence, this is how we can factorize the probability. But the problem is that to find this probability, that number, we need to know these numbers, right? So how to compute this probability? So if we assume that these probabilities are there, that is probability of W, like probability of go is there. So probability of go is say 0.03, probability of 2 is 0.08, probability of school is 0.01. Then we should also have probabilities like probability of 2 given go. So we should have probabilities like this as well. So we should have another probability table or some estimates where we should have, say, what is the probability of having the next word is go if the current word is go? What is the probability of having the next word is to if the current word is go? What is the probability of seeing the next word is school given the current word is go? And all such pairs that we can think about. So their probabilities we should have. So this is where this is how these tables can be maintained. So we have this table, we were talking about this table, and then we also have something like a probability of school given go and to. Okay, so for that also we should have some kind of table which says if the first two words are go and to, like this one, what is the probability of next word is school? This one. Or if the first two words are go and to, what is the probability of the next word is to? And like that, we should also have these kind of probabilities. So in order to be able to predict this, we should be able to have these kinds of probability estimates based on which we can compute this. Now, how to find these probabilities? One simple technique could be to use the count-based estimates. And count-based estimate, for example, we can have probability of W2 given W1, where we count the number of examples with the sequence W1, W2 divided by the number of examples with W1. Okay, so how many times for go to, probability of to even go. So how many times we have the word or the phrase go to in the collection divided by how many of times the first word Okay, W2 given W1. So the first word, how many times we have go as the denominator. That comes as the denominator. So we should be able to do this for all pairs, for all I in the vocabulary, all j in the vocabulary. For each of them, we should be able to do this. Okay, so count of W1 W2 divided by count of W1. So like that. Then if we want to find probability of, okay, let us wait for a moment when we go to other probabilities. Now, do you see any issues with this scheme, this way of finding the probabilities?
So in the
Yeah,
first,
yeah, man, please.
no worries, Avinav. Go ahead. You can ask.
Yeah. So the issues would be that if the the count is zero, so then the all the product multiplications will reduce to zero. So we should introduce a smoothing parameter like we do in the name base.
So which count is zero?
The numerator, that is if the count of number of examples where where the sequence W1 W2 occurs, if that becomes zero, so then basically we are doing the multiplication, right? The probability of go to school is equal to probability of go multiplied by probability to go. So that will completely reduce to zero. So we should introduce a smoothing in that.
Okay. Yeah, Amandeep?
Yes, sir. I think I also had the same thought actually. Yeah.
Okay. Anyone with any other points?
Sir, if the sentences are too long, then the probability values, even if every count is non-zero, it will be very small.
And sir, in case there are only joint words like W1, W2 and not single, that is the denominator would be affected in that case.
Can you explain this part? Joint words and no.
I mean pairs basically, like W1, W2 sequences. Not single word, but the pairs.
So when a pair is there, the single word will also be there, right?
Yeah.
So there could be some very specific cases like a Hewlett Packard kind of thing, where
Yeah.
typically when we have this, we'll have both. But yeah, the single word will also have a count. Most likely, this probability will be very close to 1.
Yeah.
So one more issue.
I think there
would
will be large number of parameters to count here, estimate.
Right, there will be large number of parameters, which is again a fact to be kept in mind. There is one more point. See, all these probabilities are finding probabilities based on count-based estimates. So these are statistical estimates, right? Now, and again, when we try to find the final probability for those n tasks, these are some very basic ingredients for computing those probabilities. So we need to be very, very sure about this probabilities in some sense. However, what if W1 itself is a very rare word? Now, very rare word, W1 is rare means the denominator is very small. And when the denominator is very small, this overall quantity is expected to be very large. And at the same time, if the denominator is very small, that means we are trying to get this probability, which is nothing but a statistical estimate based on a very small number of observations. That is always very unreliable. Right? So that way, also, we'll have a lot of issues with the final probability score. So typically, any document collection that we have, there are some words which are very prominent. There are some words which are very rare, and typically, this the rare words start occurring quite soon. So that is one more problem that this will be there. Now, so we said probability of W1 to Wn can be written as probability of W1, probability of W2 given W1, probability of W2 W3, given W1, W2, then W4, W1, W2, W3. Now, what if we want to use this for finding the probability? So suppose our sentence is probability the test match between India and England is being held in Karachi. So for this sentence, if we want to find the probability following this chain rule, and what are your suggestions? Should we use this chain rule to find this probability, or are there any things to be concerned about? So can we use this?
No, we can use log on both sides. Because the multiplication values will reduce to very small numbers.
Anyone else?
Sir, maybe Ranchi would be problem in some sense because the entire sentence is correct. But let us say if we have Rajkot instead of Ranchi, and if we don't have Rajkot in our training examples, then it will lead to zero probability even though the sentence is correct.
Okay. Anyone else? Maybe we'll wait for one more answer and then we'll proceed to the discussion.
And for here, every probability is a joint probability of counting to one in a way, because every word is coming as one time. So like say for example, uh, uh, if if we look at test match, so the match is there's the match, the count of match is one, and similarly the test match will also be one. So which means it gives a high probability that this is the only way we can have this sentence formed.
Okay, so these probabilities actually are learned. The probabilities that we saw in the table. So these probabilities are learned from a very large collection, very large corpus. So it's not that we're finding these probabilities from this sentence. Otherwise, this probability will always be one, as long as we have unique words. So that's not the thing. I mean, these probabilities are estimated from a large collection of documents. So suppose you collect, say, 1 lakh documents. You can either download from, say, use some existing corpus, or you can go to a newspaper website, you crawl the different pages which exist there. You can do some basic pre-processing to extract only the textual content and remove advertising and so on. You can go to a collection of patent database, download patents, extract the abstracts of the complete text. So this becomes your collection, and then in that collection you check how many times the word go is there in that collection. Suppose 3,000 times the word go is there, and out of them, in 328 times after go we have 2. So the probability then becomes okay, these 3, so here it will come like this, and then something like 0.109. So that's how we'll measure the probability. So these probabilities will come from a large collection. That is one thing. Secondly, the other observation that some of you made, that we are multiplying many such small probability values together, the value, and then since each probability is again less than 1, we are multiplying many numbers which are less than 1. The final resultant product will actually be very small. So that is also one concern, and one remedy to that will be to use the log, and log of products is the summation of logs, so that problem will go away. Next, I think there was, yeah. Now, one more problem that I see from here is that, it came as an answer to my previous question of having this as the the estimate, is that if the denominator, if numerator or denominator are very rare, right, the estimates become unreliable. Now here, we'll have to find the probability of Ranchi given this entire thing which comes below it, before it, right? Now, since we are talking about count-based estimates, it's very rare that in our entire collection, irrespective of how many documents we have, this entire thing is seen. Is very rare. So the denominator and numerator both will be very small, and this estimate will be very unreliable. As a result, the final probability that we get will also be unreliable. So that's why, we should not use a full factorization like this. The other point that one of you mentioned is that, so for this PW1, we have a table like this. Then for PW2 given W1, we have a table like this. Then for PW3 given W1, W2, we have a table like this. Right? Now, if you have n number of words in your vocabulary, what is going to be the size of these tables? How many values we have to store here?
N factorial?
No.
2 power n.
Sorry?
For n words?
So let us assume that we are only going to see how many values of PW we are going to store. If there are n words in the vocabulary, so this will be n. And how many of this sort? W2 given W1, how many entries should we store in this table that captures W2 given W1?
N choose
W2 into W1.
N square.
N square.
Right. Then how many for this one?
N cube.
N cube. Right.
So on.
And so on. So, but our sentence lengths can be arbitrary, right? So Wn given W1 to n minus 1. So suppose, this W1 has n choices. Each of these have n choices. Okay, let me say that there are too many n's here. So there is this capital N, okay? Number of words in the vocabulary is capital N. Then for each of the 1 to small n, we have n different choices. Total number of choices becomes capital N to capital N into capital N up till n times, is capital N power n times. So which is actually huge. So even in this case, how many words are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we need to have probability of W11 given probability of 1 to 10. Right? Each of these can have n choices, and these also have n choices. So n power 11. These many entries we need in the table to be able to compute this one, which is definitely not possible. So we should not go for a full factorization like this. So we should decide that, this entire thing we can approximate as PW1 into PW2 given W1, or maybe PW3 given W1, W2, and maybe something like this. We should not go beyond. So that way, two things. Firstly, we restrict the number of small values that we are working on. Secondly, our storage we can manage better. Thirdly, the estimates that we get will possibly be more realistic and more reliable. So when we use only these kinds of things, W1, probability of W1, this becomes an unigram model. This becomes an unigram model. Uni means one, and here gram means say world. So we are checking the probability of one world. Now suppose we are also using this one along with the unigram. So that becomes bigram model. Bi means two and gram means word. So we're checking at two words. So go and two go. Third one we'll just ignore. And then suppose we are saying that in the third one also we should use. So that becomes trigram model. Tri means three and gram means in this context word. So yeah, three words together, their probability is PC. And then we can also have four that becomes quadgram. So this is how. So now we make a conscious decision that even if a full factorization is possible, we'll go to only bigram or trigram or quadgram. So people saw that after 5 grams there is typically no benefit. In fact, the problems outweigh the benefits that we get. And in most real cases, people try to go till trigram. So computes reduce, storage reduces, and we get reliable estimates of the probability. Okay. Now, for this one, for this word, let me see if there is a blank space somewhere. So here, if we want to predict, we will use probability of the and probability of test given the probability of match given the test, then probability of between. So we are using trigram model. So before between maximum we'll have two. So test match. Then for India, probability of India given match between. We will not go beyond that. And like that till we have Ranchi, but for Ranchi also the previous two words will be held in. So like that we'll find the probability, and that we will report as the probability of this. Okay, any questions here? All right. So this is how the probability can be estimated. But then the other problem that came is that what if some of the probabilities are really, really very small? Now,
so I think we have not much reduced the number of parameters still, right?
No, we have. So if you look at the number of parameters, and so here we'll have n for unigram, n square plus n cube.
Okay.
So what is this parameter? It's something like
it is big of
big of n cube, right?
Yeah.
On the other hand, if we have the entire thing, it's much bigger. So big O of n cube. Okay, so these probabilities will be using the maximum likelihood estimate probabilities, which are nothing but this probability of I wi given wi minus 1. We saw this, the counts. However, the other problem that was raised was that if we have some probability which is very less, then the entire thing due to this product comes very low. And secondly, the estimate is also not very reliable. So we need to do some kind of adjustment there to make sure that does not happen. So one way to deal with that is by using smoothing, and one typical way in which this smoothing is done, one of the very simplest techniques is this add one smoothing. So originally the count is count of wi minus 1 wi is pair divided by c of wi I minus 1, the previous word. So if this one is very small, we want to get rid of that. So for every word, what we do is in the numerator we add 1, and in the denominator we add number of words in the vocabulary. So original probability that we had now gets transformed into something like this. Okay. So add 1 because we are adding 1 in the numerator. Can anybody give the reasoning of having this plus v in the denominator?
We are reducing the overall probability by increasing the denominator.
I think that we can do in many ways. Why this specific of plus size of v?
It will basically resolve that problem, that we had with the very rare words, the issue that we had with the very rare words. So
okay, let me
compensate with it.
let me say instead of this, instead of v, suppose we do something like we add v by 2. Will it be okay?
Sir, is it to ensure that the sum of all the probabilities is 1?
Yes, yes. Yes.
Okay.
So let us, instead of I minus 1, let me only write w1, w2. So let me erase this part so that I get some space. Okay. So suppose we are having w1 and w2. So probability of w2 given w1 equal to count of w1 w2 by count of w1. Now w1 is fixed because it is given. Okay, so it's a fire drill which is happening. So w1 is given, and we are seeing for different possibilities of w2 what are the probabilities. So now for a fixed w1 for different w2s, finally whatever value we'll get by this fraction, they should be a probability value. So that means each of them should be between 0 and 1, and they should sum up to 1. Right? Now suppose there are n words in the collection, so we should have probability of w1 definitely will be there, so which is count of w1 divided by count of w1, then probability of w2 w1, which is count of w2 w1 divided by w1, then probability of w3 w1, which is count of w3 given w1 count of w1, And like that, probability of Wn W1, which is count of Wn W1 divided by count of W. And suppose in case W1 is the last word of a sentence, the next word is a full stop or a special stop symbol, and that also is considered in one of these n words in the vocabulary. So in that way, if you sum these things up, you get summation count of Wi W1 divided by count of W1, which is equal to 1. Right? So after W1, every time something or else will occur. So all those things we are counting either here or here. If W2 occurs, if W3 occurs, if Wn occurs. So whatever occurs in either of these numerator counts, it is getting absorbed. So final this summation will be 1. But now what we are doing is, for each of them, we are adding a plus 1 in the numerator. So when all these summations added to 1, it becomes a probability, nice and simple. But now, since we have added 1 in the numerator, for how many words? I equal to 1 to size of v, which is equal to n. So that means the numerator now becomes I equal to 1 to v c wi given w1 plus this one I'm taking outside, 1 is getting added these many times, divided by summation cw1. Now this entire thing is what? cw1. So that's why this earlier thing was a probability, this summation. So numerator is now cw1 plus size of v. So to make it a probability, we should add a size of v in the denominator also. So that's why we add this size of v in the denominator. Is that clear? So that this entire thing after the adjustment remains a probability. Yes.
Sir, can you please explain this part once more?
Okay. So let us see if I can have a blank slide somewhere. Yeah. Suppose our our vocabulary has words like today is rainy, sunny, windy. Now there are 1, 2, 3, 4, 5 different words in the vocabulary. Now we want to find the probability of something given today. Okay. Now what are the different choices of x? This x can be today. Any word from the vocabulary can actually come here. Is rainy, sunny, windy. Yeah, sorry, there was a call. Okay, so I think it got used. So our vocabulary is today is rainy, sunny, windy, and we are interested in probability of X given today, and X can be any of the possible words from the vocabulary. Today is rainy, sunny, windy. So for this one, we'll find the count of today being followed by today divided by count of today. For this one, we'll have probability, count of today followed by is divided by count of today, and so on for rainy, sunny, and windy. Now, if you add all these probabilities, so my claim is that each of these things is a probability. Why? To make it a probability, there are two conditions to which need to be satisfied. Firstly, they should be between 0 and 1, right? So since we are talking about two counts can be positives only, so they are positive. First part is gone. Secondly, positive means greater than 0, greater than equal to 0. They should be less than 1. So that is definitely true. So if the first word is today, the second one will be any of these 5 words. So yeah, so this count of today being followed by today cannot be more than the number of times today appears. So each of them is less than 1 also. Now if you sum them up, so let me just write it as this is X, this is W1, this is W2, W3, W4, W5. So the summation of probability of Wi given W for I equal to 1 to size of V, which is 5 here, is equal to count of today followed by Wi divided by count of today. Now every time today is there in the collection, the next word will be either today or is or raining or sunny or windy. Let us assume that okay, there can be a today can be the last word. In that case, we also have a special word like top. In that case, size of vocabulary will increase by 1. Let us ignore that case for the time being. Now, if we add all these up, okay, I equal to 1 to V. Now this summation means since the denominator is same for all these, right? Denominator is same for all these. I can take it outside. It does not depend on I also. So I can push the summation to the numerator. So it becomes like this. Now, what can you say about the numerator now? After this summation, what will it be? My claim is that it will be same as count of today. So after today, either of these things will be there. So this total summation will be same as count of today. So if this appeared in 100 documents, maybe in 90 cases, this was the case. In 90 cases, sorry, in 2 cases, today was followed by today. In say 90 cases, today was followed by is. In 7 cases, today was followed by rainy, and windy and sunny. Suppose those counts were 1 and 1. Let me change it to 6. So if we add all these up, they become the number of times today appeared in the collection. Now what we are doing is, so let me know if there is any doubt till this part.
Yeah, this is clear.
Okay. Now, what we are doing in the advanced smoothing, we are adding a 1 to the numerator. So that means each of these probabilities will have an additional +1 in the numerator. We are trying to see in the denominator also should there be something. Now, since we are referring to that as PWI given W, so now it becomes count of today followed by WY plus 1 divided by C today. Now again, if we do the summation from I equal to 1 to V, let us push this summation here. So there, this entire thing is under the summation, inside the summation. So we say that, okay, this becomes I equal to 1 to V count of today plus this 1 is being added this many times, 3 of today. Denominator remains the same. Now, if this is the case, we see that this is no longer a probability. So denominator is count of today. The numerator has so this thing will go away because this summation over all i's becomes 1 today. So to make it 1, we need to have a plus this thing in the denominator so that it remains as a probability. So that is the reason when we do add 1 smoothing, in the numerator we add 1, in the denominator we need to add the vocabulary. So which is nothing but for how many cases in the probability we are adding 1 to the numerator. So that entire mass, additional mass that is going to the numerator, we need to put it in the denominator so that the ratio, which is nothing but the summation, remains as 1. Is that clear, or there is some ambiguity?
So, so since we are modeling a language or an exact instance, so in the bigram model, shouldn't we consider only consecutive words?
Yeah, consecutive only. These
So,
are all
but here,
consecutive.
okay, but here we are considering every combination.
No, with the sequence W1, W2, not all combinations. So W2 should follow W1. There
Yes,
should be
but okay. So in example also we are following the same.
yeah. I mean, it was a very bad vocabulary. So for today and is 90 times. Suppose there were a few other cases where, yeah.
Okay. So we are presuming that there are other cases as well in this.
Yes.
Okay. Got it.
There can be lyrics of music and other things where things can be repetitions and various other this thing can be there. So there is a chance that other non-probable things also come up, show up.
Okay.
Okay, any doubt here?
Sir, this dividing where we now it's making the probability even much smaller, right? So if the size of the words are billions, now the probability is going to be even smaller, and now it's not it's not the true probability now, right? Because if you see in this case, there is a today is, and that probability will be 1 because in your vocabulary today is exist, and there is also a count of today, so that is 1. But in this case now it will be 1 divided by total number of those. So
yeah.
Is this not like skewing your probability towards one side?
So this is a very good observation. So if your collection is such that there are many terms in the vocabulary and your collection is actually not very large, then these kinds of things will be there. So that's why people say that instead of add 1, can we have add k smoothing where k can be less than 1 also. So our numerator now in this case will become C wi minus 1 followed by w1, they appear consecutively, C of wi, and instead of add 1 we'll add k here, right? Can you suggest how the denominator should change?
K into V.
Exactly.
Yeah.
K into cycle. And based on your knowledge of the corpus, you can select what the value of k should be. Say, if you feel, you can also change set k to say 0.1. So this is based on This can be a hyperparameter. Based on your domain knowledge, you can say, okay, I'll go ahead with this value of k.
Can you please repeat that skewness part with address smoothing again?
So what he said is that our original probability, say this one, was easier to follow, right?
Mhm.
But now once we have added +1 to numerator and +b to the denominator, suppose in your collection today was 100 times, out of them 90 times it was ease, fine. We could get the probability as 0.9. However, suppose your vocabulary size is 1000. So what will happen is you are making your numerator 91 and denominator becomes 1000 plus 1000. So 91 by 1100. So originally the probability was 0.9 and now becomes very, very small, right? Point what 09
Mhm.
or 0.009.
Yeah.
So this is very small. So that means we are dragging the probability very close to 0. We are reducing it significantly by doing this modification. So how justified is it? So that was the question.
Okay.
Okay, so that's why instead of add 1, we can use add k. All right, so this is one smoothing technique, and there are many various other smoothing techniques as well. So we were talking about this thing, right? This full factorization of W1. So many times what we'll see is that if you have a large corpus, even if we restrict ourselves to trigrams or 4grams, we may see that probability of a word given the last 2 words, even this we are not finding enough support for this. Suppose W2 W3's combination was not seen only, then also that problem will be occurring. So one way to deal with it will be the smoothing anyways. I mean add one smoothing or something like this. So numerator you add 1, denominator you add uh, accordingly. So in this case you can determine what should be there in the denominator. Another option is that people say back off kind of stats. So use n-1 gram statistics if n gram statistics is not available. So suppose W3 given W1, W2 is not available. Then you estimate it, you say that okay, my PW3 will be same as this trigram, right? The bigram estimate. W3 is bigram estimate, like this. Okay. Now suppose PW3 given W2, like rainy given today, even that is not there. Then you say, okay, instead of this, I'll go one level down. So this is the unigram probability of rain. Only that I will use. So back off says you are trying to find the n-gram probability or n-gram statistics. If that is not there, you use n-1 gram statistics in place of that and keep doing it recursively. Okay, if trigram is not there, use bigram. If bigram is not there, use unigram. And then the other suggestion is that you can use interpolation, where you mix different n-gram statistics. So if for this trigram, we said that W3, W1, W2. If that is not there, you use W3 given W2. If that is not there, you use W3, right? So in interpolation, what they say is that suppose you are using the trigram stats, that means you are doing like, yeah, till this point, the remaining part you are ignoring. Then for this trigram probability, you say that I'll multiply this with some factor alpha 1, I'll multiply with some factor alpha 2, this one with some factor alpha 3, okay, and this will be my trigram probability. So it is not hard falling back to the previous, but instead of a weighted combination of all. And this, or say to be to follow the notation in the slide, this should be lambdas. And they say that these lambdas can actually functions of these two things, say W1, W2. So if they are very rare, then lambda 3 or lambda 2 can have higher importance. And if they are very prominent, then we should actually rely on this and we can ignore the rest part. So this we can give more importance to this trigram probability only. So in interpolation based techniques, you mix different n-gram statistics or probabilities, and this interpolation weights W1, W2, W3, etc. will be context based. What is the context? The observed gram. So this will be function of this one. Now what function, how to do that? Again, that remains with the developer or the decision, the person who is using this. So that way also, if this probability is 0, we'll get some mass from here or here. Okay, so these are back off and interpolation, and yeah, these are actually simpler things. And now we'll go to the next smoothing technique, which is called good Turing smoothing. So here what happens is that we will, if you look at the left side diagram, so f is frequency. So for any n-gram, so it can be unigram, bigram, trigram, whatever, if we try to count the frequency, most likely we'll be seeing some with frequency equal to 1 and some with frequency greater than 1. Say suppose we are talking about unigrams. So there are some unigrams which are occurring one time, and there are some unigrams which, and the rest of the unigrams are occurring more than one times. Right?
Sorry
So,
to interrupt, sir. I think the slide is not changed. I can still see the back of and interpolation.
okay, so let me, yeah. This one. Okay, so suppose we are talking about, yeah, thanks for pointing that out. So for any gram, say unigram, bigram or trigram, if we look at the, for each possible gram, what is the frequency? So we'll see there are some which are having frequency 1, there are some which are having frequency more than 1. Let us talk about unigrams. Some unigrams are occurring one time, some are occurring more than one times. So what is said here is that the total mass, total frequency mass which is there with frequency equal to 1, that entire mass will transfer to the ones for which the frequency is equal to 0. Okay, and since the probability everything should sum to 1, so for the remaining, whatever is remaining from that, will h out some portion for f equal to 1. So we'll readjust the probabilities here. So essentially all probabilities get modified. So there are some n-grams for which frequency is equal to 1. So that entire probability frequency mass will transfer to the ones which have 0 frequency, and whatever is remaining, that will redistribute among the existing non-zero frequency wala n-grams. So some of them will be coming for the words which, yeah, so they will come, and the remaining also will be redistributed. So if we look at the parts where the probability mass for the n-grams with frequency equal to frequency non-zero, so there, that those are the seen n-grams, so their probabilities, some of their probabilities, the sum of the unseen probabilities, they were 1, right? And this entire thing was n by n, and that's how this was 1. And now what we will do is, I think next slide will explain it. Need to assign probability to the unseen words. Second. So let's put not. Huh. Yeah, so this is called good Turing smoothing. So we need to assign probability to the unseen words, otherwise they become 0, and the purpose smoothing is to assign some probability to them, right? So, so it is equivalent to reserving some probability to words with frequency 0. Unseen words means frequency 0 words. So what we do is we bin the words according to frequencies. Okay? So suppose this is the set of words for which frequency is equal to 1. Words means n-grams, say. But for simplicity, I'm just saying words now. Then there is a set of words for which frequency is 2. There is a set of words for which frequency is 3. Set of words for frequency C. Set of words with frequency n C plus 1. So what we do is transfer mass from one bin to the previous one. So total frequency mass of N2 comes to this bin. Total frequency mass for N3 comes to words in N2. Total frequency mass of words in NC plus C plus 1, that comes to this bin. And now we recalculate the effective counts. So earlier, suppose the total number of, if we talk about unigrams, the total number of tokens T was equal to summation I, summation total token count for count equal to C was
Summation of all n1 to nc.
yeah, so the total will be like T1 plus T2 plus like Tc plus 1, which means that words which are occurring 1 times, for there the total token count, words which are occurring 2 times, for there the total token count, and so on. Right? Now the words, suppose there are n1 number of words which are in T1. N1 number of words which have frequency 1. So this T1 is equal to n1. Right? Now suppose there are n2 number of words which have frequency 2. So from there we get 2 into n minus 2, 2 into n2 tokens. Right? There are n3 words for which the frequency is 3. So from them we get these many tokens like this. So now what we'll do, so if we now look at the total probability mass which is there in the bin for this one, for there the total probability mass will be 2 into n2 divided by t. The total probability mass which is there for this bucket will be 3 into n3 divided by t. Total mass which is here will be c into nc divided by t, and like that. So the moment we see that the total probability mass, since the denominator remains the same, probability mass and frequency mass, these two things we are using, I'm using interchangeably. So this, the total mass for this bucket, which is this, if it comes here, that means this entire probability will be distributed among the words which are here. Then can you tell what will be the probability associated with each word here? It will be 3 into n3 divided by t. This was the total mass which is getting distributed among n2 words here, this one. So this is how we transfer mass from one bin to the previous one, and we can recalculate the effective count. So the next slide should have it. So typically the probabilities are nothing but count by t, right? Now this count is getting adjusted to this one. Now here we had C plus 1, these many words. Their total mass was, so there was C plus 1 words. Each one is appearing in C plus 1. So these many is the total token count out of the total T. Now this, when it comes here, it will be, this entire mass will come here. And now this entire mass will be distributed equally among the NC number of words. Right? So with each word, the count and the probability which is proportional to it will be, in the denominator will have NC, because this entire mass is getting equally distributed among them. Okay. So the effective count now for a word which had frequency C will become C plus 1 into N C plus 1 divided by, if the count is this, the probability will be this thing divided by 2.
NC.
So next one, the next slide actually gives this thing mathematically. The probability mass of all words that appear k minus 1 times. So we used here C and C plus 1, and here next slide says k plus 1, sorry, k minus 1 and k, essentially the same thing. So it becomes k into, this becomes the effective count. So if we go through this slide and try to understand each point, the probability mass of all words that appear k minus 1 times, that becomes, so earlier, so GT means good Turing smoothing. So this is also one kind of smoothing technique. The original probability, we are modifying it. So their total summation, probability of GTW, and this summation over all words such that their count is equal to k minus 1. Now their summation now is equal to, since these counts are now coming from the next bin, right? So the summation remained, now it becomes for all words W prime for which the count was k, because we shifted probability from k bin. And what was their MLE estimates? Now for each of those words, the probability was k divided by n. It is appearing k times out of n different tokens. So in earlier slide, I used T for tokens. Now their total mass becomes k into nk divided by n. Now there are nk minus 1 words that occur k minus time in the training data. So for all of them, we are actually trying to find this. So good Turing replaces the original count c k minus 1 of W with a new count c star k minus 1, and this is this thing divided, I mean this numerator, because this is a probability, so denominator n is there, but if we check the only count, so numerator k into nk divided by nk minus 1, and the probability will actually be this thing into 1 by n. This will be the probability. So people then found that good Turing smoothing is actually quite useful for many language modeling tasks, and then there were a few other, I mean not in its current form, some modifications needed to be done. So what happens is that they took a large corpus, and from there they estimated the counts and the frequencies of all the words. So suppose the number of words for which the frequency is 1 was 268. This is the frequency, and this is the frequency of frequency. How many words with frequency are? There were 112 words with frequency 2. There were 70 words with frequency 3, and so on. And 4, 5, 6, 7. Now, what they saw is that, this is not always continuous, which is expected. And what we mean by not continuous, they, there could be corpus or in this range only. So there was a single word with frequency 400, okay, and then there was another word with frequency 19180. In between, so there was no word with frequency 401. There was no word with frequency 402. However, when we talked about this, binning and so on, we said that n1, n2, n3, nc. Okay. So for each count there is a bin. Now what happens if there is no bin for one count? So for everything here the probability was 0, but now when we are shifting this to the previous bin, for that previous bin the frequencies are and the probabilities become 0 now, which is again not desired. I mean, that defeats the basic purpose of smoothing. So they plotted it, and this is the graph that they got. Now this is one pattern which is typically observed in any document corpus. So if you plot frequency on one axis and number of words with that frequency on the other axis, it will have this kind of plot. Now this plot is on log scale. So x-axis reports log of Ri, y-axis reports log of Nr. Now, so what you see here is that this one is 1. So no word can have frequency less than 1. Right? So there is nothing below it. And then there is a big, you see a lot of gaps here. What do the gaps mean? You know, maybe word is having a frequency here, another word with a frequency here, but in between there is no word with that corresponding frequency. And that problem will be hurting this good Turing smoothing, because the entire probability mass of 0 will now be shifted to some other words. So what they told is that instead of so there are many gaps with 0 words with frequency, sorry, 0 words with frequency R, as increases, and in that case the good Turing estimate becomes useless. Now from NR we actually try to get ZR. So instead of trying to get this NR, we'll get something called ZR. What is ZR? So ZR they define as twice of NR divided by T minus Q. What is T and what is Q? So they say that T, R and Q are frequencies such that they have non-zero count, and Q is the immediate next frequency after R for which I have a non-zero count of words, and T is a frequency immediately less than R, so that there is at least one word with that frequency. Okay, ideally, you know, when we are in the lower region of R, typically if R is equal to 2, this will be T, this will be Q. If R is equal to 5, this will be T, this will be Q. So between Q, I mean, T will be R minus 1, Q will be R plus 1 in the lower range of frequencies. That means Q minus T will be equal to 2. So that's why in the numerator they have added 2 into, and the denominator is T minus Q. However, as we go to higher ranges, so there might be some gaps between R and Q, and there might be some gaps between T and Q. So Q minus T, this will be much more larger than R, larger than 2. So that way, this will be, this will be larger than R. Now this is the ZR, and then they try to predict, they try to model a relationship between R and ZR. Okay, relationship between R and ZR. They use a simple linear kind of relationship where they in the log space, log ZR equal to A plus B log R. And once they have a collection, you can have R, NR and corresponding ZRs. It becomes easy to learn the values of A and B. And for any R now, you use this fitted value to make use of in your frequency calculation. So for any, this one, you can find nk minus 1 based on this. Okay, so for large R, you use this value. It's called simple good Turing. And when R is small, you use good tuning. So that's how the smoothing can be done. So original NR versus RI, this was like this, and ZR versus RI. So this became in the log space, it became like this, and you can see that there is a very clear linear trend here. Right? So all these missing values can actually be used based on this formula. So in that way, we can get the probabilities. You can use them now for language modeling. Any questions here?
Sir, in this case also, your this fitted one, that also will give this some of the values which are having frequency 0, right? And then once we transfer, we'll have same problem.
No. Now this A and B will be non-zeros. So this line will be there. So we'll not get 0 value here. There will be some
No,
value on
not
this line.
okay, but the frequency value, whatever it will provide, like this R, that might have some 0 frequency, right? In your first frequency table itself.
See, from our collection, we construct this table, R in R, and we also construct ZR based on this calculation. Now we use this to find a mapping between R and ZR.
Yeah.
Okay.
So
And if the for smaller values, we directly take the values from here. I mean that smaller values we can define. The till the time we find R values to be continuous, we use this. The moment we see okay, some gap starts to come, from that point onwards, we can use this estimate. And here we'll not have zeros.
okay, so my understanding was here that once we use this one, because we are having now mapping from R to ZR. So are we using just in the ZR space for higher frequency? Now we are not using the R space. Is that correct?
From R to become so from R we come to ZR and we can go to NR. R remains the same. R remains unchanged. Interpretation of R or interpretation of K remains unchanged. But this NK and NK minus 1, instead of that, we get these modified values of it based on this learning, this pattern.
Okay. One more question, like for every bin, once we redistribute from the next bin, like we transfer the mass from the previous to this one, and I mean, will that not have any effect on the like distribution of this, like probability? Because now we are bringing the next one to the previous one, so we are
no, that will not be there because of this thing. So we know that all words, say suppose there are 20 words with frequency 2 and there are 10 words with frequency 3. Now if you look at, and suppose there were some 1000 words in the entire collection. Now for each of these 10 words, the probability was 3 by 1000.
Yeah.
Right. And for each of them, the probability was 2 by 1000.
2 by 1000.
Now this total probability mass here will be what? 3 into 10, because there are 10 such values by 1000. So that is 30 by 1000.
Yeah.
So this is nothing but k into nk. This k equal to 10. Sorry, k equal to 3, nk equal to 10. Now this entire mass we are shifting to here.
Yeah.
So now we assume that for all the 20 words, total this probability is 30 by 1000. Now each of them get this entire probability mass divided by 20. So that becomes 3 by 2000. So which is k into nk by
it changed, right? Now it became 3 by.
It changed. So this is the good Turing smoothing. So there can be one can also combine the MLE estimates with the good Turing estimates. Even that option would be there. But good Turing says you simply use this one. No need to use this MLE.
Okay, sir. Thank you.
So this probability redistribution, is it happening recursively?
Not okay. Recursively means from bin
Like
4 to bin
yeah,
3, bin 3 to 2.
yeah.
But for each bin, we are computing it once only.
So if we want to compute P1, so in that case, does the redistribution from P3 to P2 is required, or simply compute P1 by taking original values from P2?
So we need to do it only one time by taking from the next. So I got your question. So you are saying that, so for getting n2, we are getting from, I mean, for n1 we are getting the values from n2, but n2 will come from n3. So
Yes.
once from n3 we get n2, after that do we recalculate and assign to n1? Answer is no. We do it only one time.
But here also, sir, like for words which are not there, unseen words. So again, the zero probability question is still there.
No. So yeah, I should have been explicit here. So for this n0, it comes from n1.
Okay.
Now,
But sir, when we
so this is the thing. So for frequency, let that slide come.
Then what would be n0 in that case?
So for f equal to 0, we get the values from f equal to 1. That is what is happening in this. So for n equal to 0, the counts in 1, that is coming. The
are
problem
we
is that,
directly going to
please go ahead.
so, sorry, my question was same thing here. Like, are we directly going to use, or we are going to redistribute over n0? Because there is no n0, then how do we redistribute it?
There is no n0.
Yeah, I mean, zero frequency word is not there, right? And earlier we were redistributing like this one to the n, like n2 we redistributed to n1. How do we redistribute n1 to n0?
This one. So for the 0th bin, now the count will be c star 0. So that means k equal to 1. So this will be k into n1 divided by n0. This n0 can be estimated with something. So that will be the total probability mass comes to here. So one thing is that we do not know how many are there in n0. So this total mass to be distributed over how many? Is that the question? How many words?
Yeah,
Yes, sir.
how do we know n0?
So we
How many
say that
words?
since we do not have any way of knowing how many unseen words are there, we can simply use that one as a probability divided by, sorry, whatever was there for n ones.
Okay, okay, understood, sir.
Okay. Okay, so that was for today. In the next class, we'll start a new topic. So any, yeah, so we'll also see how it can be used for evaluation, this language modeling and language modeling probabilities. So that will start from there in the next slide. Now, so let me exit from here. Some of you have also requested for the LSEM timetable. So let me just tell you the first Saturday on the exam slot. I think the date is 17th. So this one. So the exam slot is from 27th April Now this 27th April, which happens to be a Saturday, we'll have the exam, physical exam on that day, 27th. We'll just check the room availability, and we'll start it maybe from 11 a.m. If the room is not available, we'll just see. We can shift it either ways by half an hour or so. So that's the thing.
Sir, I have one request for this final exam. I am not in India. I for me it takes like 3 lakhs of rupees